Okay, so this is going to be, hi, so this is going to be the first video in chapter 24. I decided to do a little different this time and just look at some screenshots of the book because this shouldn't take as long. I also wanted to encourage you, make sure you watch that MIT like 7-minute video on double slit and on the double slit experiment performed by Young. I think it has some extra stuff. It also has like a demonstration, which we probably won't be able to do in class for money reasons. And I think it's really good, so make sure you watch that. It's got some really good stuff in it, and some better diagrams than the book even. So anyway, enough selling stuff for MIT. Um, I wanted to talk a little bit about this. MIT has a much better diagram than this top thing. I think I even said that in the reading guide. But let's just go through why you have this equation down here. Why do you have that equation representing the spots where the light interferes constructively when you shine it through a double slit? And you get that pattern. So why is it d sine theta, where d, remember, is the distance between the two holes that you make? Um, Theta is the angle that the light comes out of the holes at, like referenced from this straight line, and m is like a certain value where it's the first order, the zeroth order, where I like to think of it down here. Like if you look down here, the zeroth order is always going to be the brightest, the most intense light, and then the one order, it's equal sides from that, and then the second order is a little bit less intense. You can see how it's dropping down in terms of the like y-axis here. The y-axis on this guy is light intensity, so I should really put like an I there. Okay? But anyway, that's what the M means. And remember, lambda is just the wavelength of this particular kind of light that you're shining through, whether it's like infrared light that you couldn't see, or green light that you could see as green, or yellow light, or whatever you have. And you'll look at those in a second, colors in more depth. So anyway, why is this relationship true? I think if you look at this triangle up here, you can see it. They talk about it, but I don't know. It was a little unclear to me. So just look at this little gray triangle that they have. Can you see it right here? I'll enlarge it off to the side. So let's pretend that that triangle is over here. So let's label the sides of that triangle. This side of the triangle is D, right? So we've got D being that side of the triangle. Looks like we made it to where it's a right triangle. So this is a right angle. And what else do we have? I think they're saying that the extra distance light has to travel there is that. So let's see. It says the extra distance traveled by the lower ray, that's like this little extra distance right here that you can see, that little extra distance that lower ray has traveled. They're saying that's d sine theta. So they're saying constructive interference will occur and a bright fringe will appear on the screen. So what are they talking about? I think they're saying like this light ray right here travels a little bit farther than this light ray up here, and the extra distance is going to be d sine theta. So they're saying when constructive interference occurs, that little extra distance is equal to some integer multiple. That's what m is. It's an integer multiple of the wavelength of that specific light. Does that make sense? So that then you have like the wave crests lining up from this above light ray and this below light ray. When those wave crests line up where it's an integer multiple of the wavelength, um, that's where you get constructive interference, which turns out to look like a bright patch, like the little bright laser beam in the MIT video or what have you. Okay? So I think that makes pretty good sense. The only question is, why is it d sine theta that's this little extra distance here that that lower light beam travels? So let's just look at the triangle. So this is the theta, right? So let's just verify that. Basic trigonometry, but it's good to verify, I think. So they're saying that this side over here of the right triangle, this leg is d sine theta. Well, if you take the sine of theta, let's just call that x for now. Let's pretend we don't know what it is. Then we'll say, oh, I can't write off to the side. I'm running out of space. I guess I'll just try to shove it in here. So if we take the sine of theta now, let's see. Sine is opposite over hypotenuse, right? So we go opposite theta is x, hypotenuse is d, so doesn't that mean that x, if we multiply the d up here and get rid of it over here, isn't x d sine theta. So I think we can see that that little extra distance on that triangle is d sine theta. So that was just me talking a little bit about why that works and why you get bright patches where you have an integer multiple of the wavelength equal to the spacing between the slits times the sine of theta. It's kind of a crazy relationship, but it does make sense. It does, just a little tiny bit of geometry, really. Okay, let's see what else we have. We already talked about how the in this kind of experiment, the 0th order light band, that one right in the middle, that's going to be a little bit brighter than the others because of the wave intensity is becoming the most there, and it kind of falls off. And so you can even see in this little bad picture over here, this black and white, that these ones are not as bright. Even like for instance this bright patch. Oh my gosh. Or this bright patch is pretty bright, but you can see even between those two there's a difference, and that's because the intensity is falling off from here to there. Okay, so just talking about that, remember you also have destructive interference. You have a little equation. It's pretty much the same thing as that other equation, except it'd be m times the wavelength for constructive interference. So you say if you just add like 0.5 to that m, right in the middle, that's going to be the middle of your dark band each time. So this is just saying instead of going integers, go halves, and you get the middle of each dark band. Okay, so that's pretty simple, I think. All right, let's look at the examples they had in this section. I didn't think they were too bad, but my God, our cat's racing. Anyway, let's see. So this one says a screen containing 2 slits is 0.1 meters apart, so that's like D. So let's write down our givens. I really don't like the way the book shoves so much information in these examples. That's why I do most of them for you. So let's practice reading this. So we got D, and it says containing 2 slits is 1.2 meters from the viewing screen. So that's this distance. You can see it down here. It's 1.2. So this little distance is really tiny, 0.1 millimeters. If you watch the MIT video, they're going to talk to you how about if you do any double slit experiments in real life, you got to make sure those slits are really, really close together. So 0.1 millimeters, that's really close together. Anyway, so they're saying the type of light that hits is 500 nanometers. I think that falls in the visible spectrum. Learn about that next. Approximately how far apart will the adjacent bright fringes be? So they're asking how far apart are these bright fringes. I'm going to go back to this previous example. They're asking basically how far apart are these guys right here. Yeah, like how far apart are these? Oh, it's this distance, and it's the same for each bright fringe. Okay, so they've got that set up. You can see the band over here. You can see like the bright, 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 and then you'd have like a dark patch right in between those. Okay, let's erase that now. A little more erase. Okay, so we're supposed to figure out that distance. So first we just use the bright fringe relationship. So they've got it right here. We usually start out with d sine theta m times lambda, so we can just say that we're going to take the first bright fringe, so out 1, that would be like out this far, right? So we'll say m is 1, that's what they did. Lambda is 500 times 10 to the 9th, that's 500 nanometers. Done. Divide d to the other side, we said it's 1 millimeter, so that's 1 times 10 to the negative 4th, isn't it? So you got to put, if it's millimeters, times 10 to the negative 3rd. So we could have written 0.1 times 10 to the negative 3rd or 1 times 10 to the negative 4th. Same thing. And we get that. But that's sine of theta, right? Let's specify here. See, I don't like what the book does. So that's sine of theta. And then what they do is they use this physicist's trick. You know, I don't really like it. I'm not super comfortable with it. But, you know, I'm a mathematician. Well, I'm a math teacher, I should say. And I'm not real comfortable with them using this small angle approximation. They like to say that a lot, right? The small angle approximation is kind of like what we used for our pendulums. They're going to use it a lot in this book. I like to try to avoid it if possible, and you can avoid it this time. I don't know why you would use it. But what they're saying is as long as the 1.2 is so much bigger than that 0.1 millimeter, you can say that the sine of theta is approximately theta, and also that the tangent of theta is approximately theta. So they're making this big claim, which I think is rather dangerous. I don't know. that sine of theta is approximately equal to that, and then they're saying that's also all these things are approximately the same. And you know what? They're right, but it's just so dangerous. Let's just do it the real way. Why not? Why wouldn't we? Okay. So let's just remember that this 5 number is equal to the sine of theta. So then we go back and we look at a triangle down here and we say, hey, we want to look at this particular triangle, don't we? That says right there. And that'll give us that width that they want. So they called it x1. Okay, so it's x1. So we say theta goes in here. They're calling it theta 1. I guess I'll call it theta 1. So we've got theta 1 right in here. And we know that this is 1.2. We're trying to get x1. Isn't that a tangent relationship? So we say the tangent of theta 1 equals, what is that? Opposite over adjacent. And there we go. So the only question is multiply by 1.2, so you get 1.2 times the tangent of theta 1. And instead of using their small angle approximation, I'm just going to figure out what theta 1 is. So you can either take the inverse sine up here or down here on the same step, whatever, because the next step on this side would be to take the inverse sine of both sides, wouldn't it? So in other words, theta is the inverse sine of this. So I'm going to put the tangent of the inverse sine of 5 times 10. Is that a -3? Looks like it. The -3rd. So 5 millimeters, yeah. So you could either do that beforehand or just put it in here like this. Let's see what our calculator provides us. Make sure you're in degree mode, right? So 1.2 tangent, the inverse sine of 5 times 10 to the -3rd. And let's see, what did I get? I got 0.0. So I got 0.006. That's what they got. They got 6 millimeters. But I have a little bit more than that. A little more precise estimate is, we put, looks like 4 more zeros in between here. And then it's 7.5. So notice, they got it by using a small angle approximation and just pretty much ignoring that tangent thing. They didn't get the 0.75, the 7.5, which in this case, this problem, it didn't work out to be so much different, but in some problems it could, so I'm just saying, why not do it the right way? So, my opinion. Okay, let's look at another example. So I think we're still looking at that same diagram in this one, except it's just a concept. So it says, what happens to the interference pattern that we have up there, this thing that we see on the screen, if the incident light, so still 500 nanometers, is replaced by, okay, so what if we make the wavelength bigger? So this is lambda being bigger. Okay, it says, what happens to the interference pattern? So I'm guessing they want to know, does it spread out or what? So let's just go back to the main equation. So the main equation was that d sine of theta. And let's also remember that the bands are going to be equally spaced, so we can just look at like theta 1, and it'll tell us about all the other thetas, okay? So remember, theta 1 is defined as like the angle to the first band. So this case, it looks like it's to the way they have this drawn. It makes me look like looks like they're drawing it to the first dark band, doesn't it? I think this little. I guess it depends how you're viewing it. You know what? They're viewing it this way, so they're saying like this is the top of the intensity curve. Okay, that makes sense. Anyway, d sine theta equals what? Oh yeah, m times the wavelength. So they're saying what happens if you increase the wavelength and go up to like 500 or 700 nanometers? Maybe that's like, I don't know, like yellow to red light or something. So if lambda gets bigger, let's just see what happens in this equation. If lambda gets bigger, m's not going to be able to change, right? So I think we can kind of ignore this guy. So if lambda gets bigger, something's going to have to get bigger over here to compensate. So the question is, which thing do you have control over? Do you have control over d? No, I think they wanted d to be fixed. They didn't say to change d, did they? So we really shouldn't be looking at d either. So if lambda gets bigger, the only way this thing can stay equal is if, isn't it, if theta gets bigger? because sine of theta increases as theta increases. So I think the only thing that could happen is theta gets bigger. So let's just look at this, and what would happen if this theta 1 got bigger? If it went from being right here to being, for instance, up here, what would happen to the interference pattern? Well, wouldn't it spread out? So wouldn't the interference pattern, instead of being like bright, bright, now this bright line might move up a little bit and become a little bit higher. So then you'd have this much distance between bright lines instead. So I think that's what would happen. Part B, so I guess that's part A. Part B says, what happens if instead we leave it at 500 nanometers, but the slits are moved farther apart? So these guys are moved farther apart. Remember, that's D. So this time we change D. So once again, start out D sine theta equals m lambda. M and lambda are all staying the same, so this guy is not what we're thinking about. We're going to say that theta might be changed, right? So theta might change. If we make these bigger, won't the angle at which the light comes out change? So I think D and sine theta are what's changing in this one. This guy is fixed. It's the only way that if this side of the equal sign is going to stay the same no matter what, and we increase D, so let's say D goes from 0.1 to like 0.2 or something, if D gets bigger, the only way that this guy can compensate so that this side stays the same, because that side's not changing, right? The only way this guy can compensate is if theta gets smaller, right? So if theta gets smaller, same thing as this one, then we're going to have this guy go purple. So theta is going to get smaller on that first band and be a little bit narrower. So now I think those bands on the interference pattern are going to be even closer together. So this one's closer bands. And the other one was farther apart. But do you see how I analyzed that? I hope you really understand how I analyzed when one thing was changing and one thing was fixed. That notion of fixed and variable is just like the most important thing you get out of high school physics and calc. It's really important. Okay, I think we had one other. Let's look at this one. This one said, white light passes through some slits, interference pattern is observed, and the first order fringe has a rainbow. Okay, so I guess I should have taken another picture. Let's have a look. So they're saying, let's go back up. So they're saying we have a rainbow on that first order slit. So like here's the first order, and you know it's like all the way from the edges of the rainbow. So they're asking us to like look at the specific colors in that now, I think. Okay. All right. So they say violet and red are at opposite ends. So should we pull that back up one more time? So you can see that like red is over here, and technically over by the blue is violet. I don't know, I'm probably colorblind, but so opposite ends of the fringe. Okay, and they say that that happens at 3.5 for red and 2 for violet. So what are we supposed to do? We're supposed to estimate the wavelengths of violet and red light. Oh, isn't this exactly what Young did to actually figure out the wavelengths of those colors of light back in the 1800s? I think this was a really big experiment. So neat problem. This is a cool one. So if we observed, so like we're looking over here, right? So we've got like the wavelengths. There's the 0th order, and then we've got like the first order peaks over here. Let's kind of try to draw a diagram. That's really terrible, but you know. So they're saying to look like out at these two. So let's go from the 0th order out. So they're saying, I think that looking at this fringe, we've got like out at the very end, the red end, we've got like 3.5 millimeters, and then this one is at 2 exactly millimeters. So that's kind of the idea here. Okay, so don't make this hard. I think you just want to apply that equation twice. So you apply the equation that says d sine theta equals m lambda, and you do it separately. So you do this for violet, and then you do it for red. You know what? Let's just do one and then take the book's word. So we're trying to find the wavelength of the light. M is 1, right? We went 1 order out, so 1 Lambda is what we're searching for. D, they told us D, didn't they? Yeah, they said 0.5 millimeters. So I'm going to go 0.5 times 10 to the third, negative third. Okay, that's D. And they tell us the angle. Did they tell us the angle? I don't think they did. We still haven't used our 2, right? So if x is 2, see, look at what they're doing here again. They're using that small angle approximation. So you can do it that way. So they're saying like sine of theta is equal to tangent of theta equals to theta. So, and then how did they do theta? So they said x equals 2 millimeters. So let's just draw. So we've got like, here's where we're going. Let's just go down to here. So here's x, right triangle, here's theta. So we know x. So what do we want? Let's recall what we wanted. Don't we want theta? So if we want to work x in there, how can we do this? Let's see. So we have L too, right? Did they tell us L? How far away is the screen? Oh, 2.5. That's what I was missing. I was like, I forgot that there's another number here somewhere. So they said this, the screen was 2.5 meters away. So now we're going to use tangent, right? So we have that the tangent of theta is x over 2.5. So that means that theta is going to be, and remember x was 2, so theta is going to be the inverse tangent of 2 over 2.5. So what is that? Get my calculator. Inverse tangent of 2 divided by 2.5. And we get about 38 degrees. So that first right fringe is about 38 degrees. 0.66. That's good enough. Okay. The book got, did they get? I don't know. So let's go back here. Let me make this smaller. I don't like what they did on this. I don't like the small angle approximation, if you can't tell already. Okay, so what did we say D was? The slits were 0.5 millimeters, so we're going to go 0.5 times 10 to the negative third. And then we've got sine of the angle we had, which was 38.66. And if you wanted to be even more precise, you could just stick in for theta the inverse tangent of 2 over 2.5, right? Remember, inverse functions in trig represent angles, so that should make sense to you. Anyway, so theta, since we've just got 1 there, we don't have to divide anything, so we just say what that is. So in my calculator, I get what did I do? Am I in the right mode? Yes. Let's see, I'm coming out with something a little bit wrong. So, what happened? Let's see. 5 times 10 to the negative fourth. Let's do it their way, I guess. Then we'll go sine of 38.66 degrees. What did I get? I did not get nanometers. Darn it. Well, I really want to make this video a lot longer. I thought this would work just fine. So is there something wrong with our calculation up there? So let's go the sine, the inverse tangent of 2. Oh, you know what? I bet I have a unit thing. Yep, I do. I knew 38 degrees sounded too big. I was skeptical. You know what I did? Hopefully you can see, or you probably already spotted it, and were banging your head against the wall while I was trying to figure it out. Is that 2.5, wasn't that meters? And this x, didn't they say that that was millimeters? So this is 2 times 10 to the negative third, isn't it? So let's do that over again. So let's see, inverse tangent of 2 times 10 to the negative third. Sorry, this took a second. Divided by 2.5. Ah, so theta is much smaller. That makes sense. 0.0458 degrees. So that's what I should be putting in right here. Is 0.0458. And you know what? I'm just going to leave it exact. I'm going to do the inverse tangent. Put that in there. So let's see. So I'm going to say sine of the inverse tangent of I love these new calculators because they're so easy to see what's happening. Awesome. So for this number, I got something slightly different. Barely. I got like 3.99 continuing. Then eventually it had like a 7 too, so it's not really continuing, but it's slightly different than theirs, times 10 to the negative 7th. So that's about 400 nanometers still, 399 nanometers for that. What was that? That was the violet, right? The red was longer. So then you repeat the same process and you get about 700 nanometers for red. So this is how Young first experimentally measured the wavelength of different colors of light. So that's pretty neat that they have different wavelengths. Okay, hope you found this useful and not too long.